Now so it's recording, so we're good. Wanted to do a couple things on electrostatics before we jump right into working some more force problems and playing with it. We've been talking about static charge, and if I've got a negatively charged rod, this is going to give me a positively charged on this side, and this is induction. So it's an induced charge that allows for things to move around, or have our charges move around. If I touch it and then have the rod move off, I get, this is now negatively charged and this is negatively charged, and that's conduction. So we get induction and conduction. But one of the common things that we have to worry about is something that we call grounding. All right? So if I have a conductor that's attaching a rod, a wire, a variety of things to the earth, because that's usually what we are grounding our stuff to, that the earth becomes a reservoir of charge. So the earth becomes a reservoir of charge, and this gives us grounding. And grounding is very, very important, because I've got to essentially disperse off built up static charge. Okay? Because that can be very dangerous. All right? Built up static charge can be extremely dangerous. So you think, for example, if I've got, and this is why we worry about it, so if I've got something that's negatively charged and I have something that's positively charged, I can actually get the charge to jump from one to the other and create a spark. And depending on my situation, it's an aircraft wing, and if that aircraft wing is not properly grounded and my tank now becomes empty, and as flying through the air I build up a static charge, I can create a spark and have my tank blow up, which is one of the crashes, one of the TWA crashes off of New York City was attributed to a static electric discharge that went through the vapor space of a volatile substance, jet fuel, that brought down the aircraft. So if you think about why charging is important, or you want to do that, and the commonplace, and everybody's seen it, right? Mostly because somebody has been smoking while they're filling up their car. But there are occasions that you get, like what happened to us last week, when the storm starts coming in fairly rapidly and you can actually feel the charge in the air. And if you have a static discharge and you're trying to fill your car up at the same time and you get a good spark, you can actually catch your car on fire. So static charge is, we have issues associated with static charge, particularly going through volatile gases. So we want to worry about grounding, and grounding is an important thing for static charge. So that was one thing I wanted to kind of review. The other thing I wanted to kind of review is, even though we've talked about it, but we didn't really articulate it, that we have the law of conservation of mass, we have energy, we have momentum, and this is both angular and linear. So we have both of those, And when we talked about those conservation laws back in Gen Physics 1, we also said, and we mentioned, and we talked about it, that we had to have those, but there was one more, and we just hadn't articulated it, and that was charge. So I get conservation of charge. And so if we look at it and kind of write it out, it's going to say the net amount of electric charge produced in any process is 0, or we get electric charge can't be created or destroyed. And fundamentally, we know that our charge is either going to be on the electron or it's going to be on the proton. And my electron is negatively charged and my proton is positively charged. And if you think about that, this is a fundamental particle of the universe. This is made up of fundamental particles of the universe. So I've got protons and electrons, and because of this, these are quantized. Let's see if I can actually spell today. They're quantized. So because they're quantized, we can actually do some calculations. And I think several of your initial homework problems are pretty much like this. So how many electrons are in a charge of -3 or -30 millicoulombs? So that's kind of a straightforward type problem. I got to convert into coulombs. And I have 1.602 times 10 to the minus 19 coulombs per electron. Negative, because that's an electron. And if I poke that into the calculator, I get 1.87 times 10 to the 17 electrons. And if I want to know that mass, just how much mass is that, I'm going to take my 1.87 times 10 to the 17 electrons, and there are 9.11 times 10 to the minus 31 kilograms per electron. This gives me something on the order of 1.71 times 10 to the minus 13 kilograms. Good? Okay. If I'm building my working cheat sheet for electromagnetics and electrostatics, we already know that F is equal to KQQ over R squared. And it's a vector, and the force is going to be along a unit vector in the R direction. We've got some critical information the charge of an electron or a proton, the magnitude of that charge is 10 to the minus 19 coulombs. We've said K is 8.99 times 10 to the 9th Newton meters squared, coulombs squared. You'll want to keep track of the mass of the proton, the mass of the proton, mass of the electron. It's 9.11 times 10 to the minus 31 kilograms. This is 1.67 times 10 to the minus 27 kilograms. And for grins and giggles, I looked it up today. The radius of the electron is 2.8 times 10 to the minus 15 meters. And another number that we use a lot is the Bohr radius of the hydrogen atom. And that is, if I have my proton and my electron, this is N is equal to 1. So it's in that first energy state. And that number is 5.29 times 10 to the minus 11 meters. And there's one other key thing that you guys need to know about. Don't tell me I didn't write it down. I have no idea. Oh, there it is. Even though that's the value of K, a lot of times you're going to see, and when we get to magnetism, we're going to see it again, K actually is equal to 1 over 4 pi times this epsilon. And this epsilon naught is equal to 8.85 times 10 to the minus 12 coulomb squared Newton meters squared. And this is called the permittivity of free space. That's the Bohr radius. Yep, that's the Bohr radius of an atom, of a hydrogen atom.
Can you slide it up a little bit?
That's the orbital for my electron, my proton. This is the first energy state. Yeah.
Can you slide it up just a little? Other way.
You mean this way?
Yeah.
You good, Charles?
Yeah.
Okay, so now we can dive back into some problems with forces. So let's do this one. I've got charge 1 and I have charge 2, and the distance between them is 1 meter. Charge 1 is going to be a positive 60 microcoulombs. Charge 2 is going to be a positive 30 microcoulombs. I'm going to put in a charge 3, but I want to put in charge 3 such that it's along the line between charge 1 and charge 2, but I want it to be in equilibrium. And my charge 3 is going to have, it's going to be an electron, or it's going to be a minus 25 microcoulomb charge. So I want to know where I'm going to put it between charge 1 and charge 2, such that it's not going anywhere. Because it's negative, it's going to be attracted to that side. And because it's negative, it's going to be attracted to that side. And so we want to find that balance point. So if I do that, one of my first conditions of equilibrium is the sum of the forces have to equal 0. And since I'm looking at it from the charge 3 perspective, okay, I'm looking at it from the charge 3 perspective, I'm going to have the force from 1, 3 is going to be negative because it's going to want to pull it that direction. And I'm going to have the positive on the other one, and this is 2, 3. So that's where I'm going to be balancing. So I can do it this way. I can calculate the magnitude of 1, 3. And I can calculate the magnitude of 2, 3. And this is going to be K Q1 Q2 over R12 squared. This is going to be K Q, well, this is going to be 3. It's going to be 3 because I'm using 3. K1 or K2 3 over R23 squared. Now, I went ahead and plugged in the numbers. I mean, you can do it a different way, right? So I went ahead and plugged in the numbers. Let's do it without plugging in the numbers and see where it gets us. So I'm going to have F13, it's got to equal F23. This is K, charge 1, charge 3, R13 squared is equal to K, charge 2, charge 3, R23 squared. Now, R23 is equal to 1 minus R13, right? If I put this is 1 meter, and this right here is R12, this right here, or R13, this right here is R23, and this is going to be this will be 1 meter minus R13, but we'll get there in a second. I've got charge 3 is on both sides, so that's going to cancel. K is on both sides, so that's going to cancel. So I'm going to have Q1 R13 squared is equal to Q2 1 minus R13 squared. So I'm going to cross multiply. I'm going to get Q1 1 minus R13 squared. Q2 R13 2 squared. All right, since these are the same, I'm going to clean this up a little bit just to make my life a lot easier. This is going to be Q1 R1, or 1 minus R is equal to Q2 R. That's all squared. So this is Q1 1 minus 2R minus R squared is equal to Q2 R squared. You guys let me get away with not squaring it. So I'm going to have Q1 minus 2Q1 minus Q1 R squared is equal to Q2 R squared. So I'm going to put everything on that side. This is going to be Q2 plus Q1 R squared plus 2Q1 R minus Q1. Now I can just use the quadratic equation to solve it. So I'm going to get Q2 was 30 microcoulombs plus 60 microcoulombs R squared plus 2 times 30 microcoulombs R minus 30 microcoulombs. So I'm going to get 90 microcoulombs R squared plus 60 microcoulombs R minus 30 microcoulombs. Just to make my numbers easy, I'm going to divide everything by 10 microcoulombs, right? I can do that, right?
Can you do 30?
Yeah, you can do 30.
Yeah, you can do 30, so this is going to be 3R squared minus plus 2R minus 1. Now I'm going to do minus, what is it? Minus b plus or minus the square root of b squared minus 4ac divided by 2a. So I'm going to get minus 2 plus or minus the square root of 4 minus 4 times 3 times minus 1 divided by 6, 2a, right? So I'm going to get minus 2 plus or minus the square root of 4 plus 12 divided by 6. Minus 2 plus or minus the square root of 16 divided by 6. Get minus 2 plus or minus 4 divided by 6. So I'm going to get minus 6 divided by 6, or positive 4. Get 1/3, right? And what that's telling us is that we have another equilibrium point over here outside and you guys have an example in the book that does something very, very similar. Okay, so let's do one that's a little more complicated. So now we're going to go into 2 dimensions. This one is going to be 15 millicoulombs. This one is going to be a negative 10 millicoulombs. This one is going to be a minus 20 millicoulombs. We're going to have 0.5 meters, and we're going to have 0.5 meters. And we want to find the force on this one. That's the one we want to find the force on. So I can do the force. The first one, I get my 9 times 10 to the 9th. And I'm going to get my 10 times 10 to the minus 3. And I'm going to get my 20 times 10 to the minus 3. And I'm going to do my 0.5 squared. And that's looking at this one and that one. And when I plug that in, I end up with 7.2 times 10 to the 6 newtons.
Why do you do it times 10 to the -3?
Milli.
Oh, okay.
Because this is in coulombs. So I gotta make sure everything's in coulombs.
You're dividing just the 10 times 10 to the negative third, and then 20 times 10 to the negative third by 0.5? Or is it, okay.
This is K, Q divided by R squared. We just write it that way by convention. Now, I will warn you guys, okay? I will warn you guys, when you're plugging, get to know your calculator really, really well, because a lot of times when you're plugging this into your calculator, you gotta be really careful. Because depending on how you square things and depending on how your calculator handles squaring and how your calculator handles stuff, I think I punched this into my calculator twice and got 2 different answers and went back and had to go, okay, let me take it step by step to make sure that I wasn't squaring the wrong things or dividing by the wrong things. And because depending on how your calculator enters in these exponents can be a pain in the tushy. So watch your calculators because it can help you or hurt you depending. So the second one, still going to be my 9 times 10 to the 9th. So I'm going to get my 10 times 10 to the minus 3. I'm going to get my 15 times 10 to the minus 3. I'm still doing my 0.5 squared because this happens to be an isosceles triangle. And when I do that one, it gives me 5.4 times 10 to the 6th newtons. Now, if I'm drawing my picture, this one becomes that force right there. This is a negative and a negative. It's going to be repulsive, and I'm looking from the perspective of this charge. So it's going to go that way. This is a negative, and that's a positive. So I'm looking at this one right there. So when I write down my resulting force, I'm going to get a negative 7.2 times 10 to the 6th in the I direction, plus 5.4 times 10 to the 6th in the J direction. So that's my resulting force. But WebAssign and your books and the homework is going to ask for what's the magnitude. So I'm going to have to do the square root of the 7.2 times 10 to the 6th squared plus 5.4 times 10 to the 6th squared. And that worked out to be, this one actually works out to be a nice even 9 times 10 to the 6 newtons. I had some nice numbers. Okay, so now if I go back up here and look at this, this is 5.4, this is 7.2. My resulting vector is something that looks like this, right? My resulting vector is something that looks like this. So the angle when I do the tangent is going to be my 5.4 times 10 to the minus or plus 6. divided by my negative 7.2 times 10 to the 6. And this gives me a negative 36.9 degrees. But if I'm looking at just magnitude, we're okay. We know this is where I'm going to be. So depending on how WebAssign is asking you the question, is going to depend on whether I give this angle or I give this angle. And something to remember is that force is equal to mass times my acceleration. And the force vector and the acceleration vector are going to be in the same direction because mass is a scalar. So if I'm wanting to find acceleration, because they'll give you the mass of the object, okay? We just gave you the charge. They'll give you the mass of the object. And if I do that, I'm going to get the force divided by mass is going to equal my acceleration. So when we start doing some of these problems down the way a little bit, don't make it harder than it is. Just remember that my force and my acceleration vector are in the same direction. Looks like I got time for one more. Okay. So when we do these things, we do these things off of pith balls. And so I have a pith ball, and a pith ball is usually a styrofoam ball that's very, very light. It's usually covered in silver paint. And I'm going to put a charged rod here. And when I put that charged rod, it's going to have the pith ball move a distance of 0.1 meters. We're told that the charge here and the charge on the pith ball is 100 of that charge right there. 100 of that charge. We have tension in the stream. The pith ball has a mass of 0.001 kilograms. We can measure this angle, and that angle is 30 degrees. I want to find T and I want to find Q. So I'm going to add a couple things. I'm going to add force due to gravity. And I'm going to add the electrostatic force. Because these are repulsive, so I'm going to add my forces. And right now it's at static equilibrium. Things are not moving. So if I do that, the sum of the forces in the x direction has to equal 0. The sum of the forces in the y direction have to equal 0. So let's do Y first, because it's easier. My Y is going to be the tension. Okay, the tension cosine of the angle minus gravity is equal to 0. I'm looking at the Y component of tension is equal to 0. I've got the X component of tension, and I've got my force that's due to electrostatics. Well, I'm going to do a mathematical trick. I'm going to get Fe divided by mg is equal to T sine of my angle divided by cosine of my angle, T cosine of my angle, which is just going to give me the tangent of the angle. So my electrostatic force is going to equal mg tangent of my angle. So I can plug in numbers, 0.001 kilograms, 9.8 meters per second squared, tangent of 30 degrees. And I can calculate that, and I get 5.65 times 10 to the minus 3 newtons. Well, one of the things I wanted is tension, so that makes it easy. So tension is just the force divided by the sine of the angle. So that's going to be my 5.65 times 10 to the minus 3 divided by the sine of 30 degrees. That gives me 11.3 times 10 to the minus 3 newtons. Now I want to find the charge. So F is equal to 5.65 times 10 to the minus 3 newtons, which is also K Q divided by 100, Q divided by R squared. My R squared, my R is equal to 0.1. We know what K is, 9 times 10 to the 9th. So now if I rearrange it, I get 5.65 times 10 to the minus 3. R squared times 100 divided by 9 times 10 to the 9th is equal to Q squared. Multiply both sides by R squared. So that's this, plugged in the number. Took this Q over 100, multiplied both sides by 100, so that gets rid of that. Divided both sides by K, and that gets rid of that, and I just plugged in numbers. And if I do that, Q I've done it correctly and typed it in the calculator correctly. This may be the number. I'm going to do that again because I'm not sure I square rooted it. Yep. Yep, I square rooted it. My notes weren't 100% clear. Okay. We're gonna do on Wednesday, so you guys can start thinking about it. We're gonna take, and this is where we throw in calculus. So far I haven't had to do any calculus, right? No calculus so far. So I'm gonna have a half a sphere here. This is gonna be a line of charge. And it's circular. I'm going to give myself some points. This is going to be a positive charge Q. And we can give ourselves some reference points. This is going to be our radius R, and there's going to be my angle. And my line of charge is going to have a linear charge density. That's what this lambda is. It's a linear charge density cosine of the angle. So it's going to be a uniform line of charge. We're going to use this as 12 microcoulombs. And we're going to use the radius as 60 centimeters. And we want to find the force on that charge. So I'm going to do that one on Wednesday, and then we're going to start defining electric field.